Hi everyone, welcome back to my channel. I am Nandini V, studying in SVC College of Engineering. I am from a CSEAI department, section Infinity, subject Mathematics 1 for CSE stream, topic RS application in public key encryption. The topics involved are Introduction to RSA, Basics of Public Key Encryption, Key Generation in RSA Algorithm Steps, Problem Solving, Security of RSA, Applications, Limitations, RSA versus Symmetric Encryption, Future of RSA, and last conclusion. Introduction to RSA. RSA stands for Reverse Shamir Adman, named after its inventors. It is one of the first public key crypto systems and is used widely for secure data transmission. RSA relies on the mathematical properties of large prime numbers for its security. The basics of public key encryption. Public key encryption uses a pair of keys, a public key and a private key. The public key is shared openly while the private key is kept secret by the owner. Data encrypted with the public key can only be decrypted with the corresponding private key. Key generation in RSA. RSA key generation involves selecting two large prime numbers P and Q. These primes are multiplied to produce the modulus n, which is used in both keys. The totient function is calculated to determine the public and private exponents. Totient means the number of positive integers less than the given integer. The RSA algorithm steps. The RSA algorithm consists of three main steps: key generation, encryption, and decryption. During encryption, the sender transforms the plain text using the recipient public key. Decryption is done using the recipient public key to retrieve the original message. So now let us solve the problem to understand the RSA. Here is the question. P and Q are two prime numbers where the P value is 7 and the Q value is 17. The public key E equals 5. If the plain text value is 6, then what will be the ciphertext value according to RSA algorithm? And again calculate plain text value from ciphertext. So the solution is as mentioned in the question, the two prime numbers are P equals 17. P equals 7 and Q equals 17. The modulus n equals P into Q, that is 17 into 7, which is equals to 119. Phi of n equals, there is a formula P minus 1 into Q minus 1. When we substitute 17 minus 1 into 7 minus 1, we get 16 into 6, which is equal to 96. The public key as mentioned in the question, E equals 5. Calculate D. For calculating the D, there is a formula phi of n into I plus 1 whole divided by E. So here I is the integer. We go on substituting the values like 1, 2, 3, 4, so on up to till when we get the value of integer value. When we go on substituting the values, when we substitute 1, we get 19.4 as the value. When we substitute 2, we get 38.6. When we substitute 3, we get 57.8. When we substitute the 4, we get 77. We will stop this here as we got the integer value. Now, the public key E comma N equals 5 comma 119. Private key D comma N equals 77 comma 119. Plain text PT equals 6. CT, that is ciphertext, equals PT to the power U. power e mod n, that is equals to e to 6 to the power 5 mod 119, which is equals to 41. This hypertext ct equals 41. pt equals ct to the power d mod n, which is equals to 41 to the power 77 mod 119, which is equals to 6. The plain text value is 6. Security of RSA. RSA security is based on the difficulty of factoring large composite numbers. As the size of the key increases, the time required to break the encryption grows exponentially. Current standards recommended using key sizes of at least 2048 bits for adequate security. Applications of RSA. RSA Applications of RSA. RSA is widely used in secure web browsing through HTTPS node protocols. It is also utilized in email encryption and design signature to verify authenticity. Many virtual private networks VPNs use RSA for secure key and exchange during connections. Limitations of RSA. RSA is computationally intensive, making it slower than symmetric key algorithms. The need for large key sizes can lead to performance issues in resource constrained environment. RSA is vulnerable to certain attacks if improperly implemented or if weak key are used. RSA versus symmetric encryption. RSA is a public key algorithm, while symmetric encryption uses the same key for encryption and decryption. Symmetric encryption is generally faster but requires secure key distribution, which RSA helps facilitate. Many systems combine both RSA and symmetric encryption for optimal security and performance. Future of RSA. While RSA remains widely used, advancement in quantum computing pose potential threats. Researchers are exploring post quantum cryptography to develop more secure encryption methods. The transition to new algorithms may take time, but RSA principles will likely influence future designs. Conclusion. RSA has helped a crucial RSA has played a crucial role in the evolution of public key encryption. Understanding its mechanism helps in appreciating its impact on modern cybersecurity. As technology advances, the continued relevance of RSA will depend on adaptive security measures. This presentation provides a comprehensive overview of RSA and its applications in public key encryption. Thank you for watching this video. Please do like and watch the video. Thank you.